standards. I kept the number and operations fractions for a week all to itself. You'll see why here in a moment. Fractions are something that many students fear. And I think it goes back to the way that they were taught, that they are separate numbers from our number line. So I'm going to go over some tips with you, not only on working with fractions in the early years, but in addition to things that we should avoid as teachers so that students have the best possible chance of enjoying fractions. So fractions have a lot of different sub-standards with them. In third grade, they start at the very basic level. Some common misconceptions that we can fix before they even begin, and some of these may resonate with you. Some of you may think that 1/4 is greater than 1/3 because 4 is simply bigger than 3, looking at whole numbers. Some may think that 157 thousandths is greater than 63 hundredths because 157 is greater than 63. Or that 2/3 plus 1/2 is 3/5 because you're adding your numerators and you're adding your denominators. Or 4 plus 3/10 is 7, or 7/10 because 4 and 3 is 7. Similarly, that 4/10 and 3/10 is 7/10, which it is, so I'm not sure why I put that one there. Scratch that. 2/3 times 9 can't be 6. Heavens no, because multiplication makes a number bigger, not smaller. Or 4 divided by 1/2 can't be 8, because division is supposed to make a number smaller, not bigger. So many of you may have seen these, and maybe these are some misconceptions you have had to overcome over time. So I am going to ask you to stop rushing the algorithms. Stop rushing to the rules that I have listed here. Stop doing that. Let the rules occur naturally. Let the students figure the rules out and discover them on their own, which takes patience, which takes time, and also makes you need to have a better, deeper understanding of why and how fractions work. So here are the rules for fractions that I'm sure you've memorized along your way in education. But imagine on top of these rules how many other rules in math that we learn. So it's no wonder that students get so confused and get them mixed up together and try to combine things that they shouldn't because of all the rules that they just want. It's not about the procedure, it's about how and why we get there. So having a deeper understanding is so crucial. So some of these that you might recall are to add or subtract fractions, you might have to find a common denominator and then add or subtract the numerators. If I want to multiply fractions, I just multiply across. But to divide, I have to invert the second and multiply. And if I want to multiply or divide a decimal by 10, we move our decimal point to the right or left that many zeros. Further, you can never ever divide by 0. And to solve a proportion, we cross multiply and then divide. So many rules, and these are just fraction, proportions, and decimal rules. Let's not even talk about algebra rules and other types of things that students have to cram in their brain. So if we allow the students to develop a deeper understanding of number reasoning or number sense, students will be a lot better off within their overall reasoning if answers are correct, if they're not, and why. Rather, according to Kathleen Kramer and Stephanie Whitney, they said, set building number sense for fractions among elementary school age students as the goal, as opposed to building procedural skills with adding, subtracting, and multiplying fractions. The first standard itself says, develop understanding of fractions as numbers. We need to start treating fractions just as any other number on the number line, a single ordinary number. Stop singling out proper versus improper fractions. They're all the same. At the same time, we need to be explicit about the importance of the unit. What are we measuring? So Mrs. R drew a picture on the board. The picture I have listed there, or draw there. Then she asked her students what fraction it represents. Emily said that the picture represents 2/6. Label the picture to show how Emily's answer can be correct. Raj said the picture represents 2/3. Label the picture to show how Raj's answer can also be correct. And finally, Alejandra said the picture represents 2. Label the picture to show how Alejandra's answer can be correct as well. So we have 3 different students picking on this picture and interpreting it 3 different ways. Let's start with Emily. Emily's answer of 2/6 means that all 6 squares together make up the whole. So all of them together are the whole. And 2 copies of 1/6 have been shaded. So this might be what you see right away, the most common one. However, Raj says that there are 3 squares that make a whole. So 2 copies of 1/3 are shaded. So there's actually 2 whole pieces here. There's the 3 little squares on the left and the 3 little squares on the right. 2 of the 3 are shaded on the left, so 2/3 are shaded. And Alejandra said 2 because she says that each square individually equals 1. So I actually have 6 whole pieces here, and 2 of the whole pieces are shaded. We cannot assume what the unit is. We have to identify the unit to attend to precision when interpreting fractions. You have to be very careful about this. The earlier we start this, the better off we'll be. We also need to stop saying parts out of a whole, such as 3 parts out of 4. This limits the range of understanding when we progress through operations. Instead, use this many copies of the unit fraction. Further, complex fractions don't make sense when we say parts out of a whole. What does 3 out of 2 mean? What are 3 out of 2 things? How can you have 3 out of 2 things? Rather, we would say 3 copies of 1/2. This will then make understanding of multiplication, division, adding and subtracting that much easier for students because it works across the board. Draw, shade, or otherwise represent the fractional part of each fraction. I want to know what 1/3 of the triangle is. So we think 1 copy of 1/3. I separate my triangle into thirds, and 1 copy of 1/3 is 1 piece of it shaded. 2/5 of the pentagon. So I think of this as 2 copies of 1/5. I break my pentagon into 5 pieces, and 2 copies of 1/5 would be 1/5 and another 1/5, so 2 of them. 3/4 of my rectangle. I want to think 3 copies of 1/4. So I split my rectangle into 4 equal pieces, and 3 1/4 would be 3 of them shaded. 7/6 of, so once I cut it into 6 pieces, I need 7 copies of 1/6. But I see here I only have 1, 2, 3, 4, 5, 6. I need 7 copies. I need 1 more, which means I need to add another shape. So by adding another shape also cut into 6 pieces, I now have my 7th piece. Which number is closest to 1/2? 1/8, 3/8, 7/8, or 9/8? I see that each of our fractions have copies of the unit fraction 1/8, so I will split my whole into 8 equal pieces. Doing this, I now can label them. So 1/8 is 1 copy of 1/8. 3/8 is 3 copies of 1/8. 7/8 is 7 copies of 1/8. And 9/8 is 9 copies of 1/8, which would place me on the other side of 1. 3/8 is the closest to 1/2. Notice in the middle there that I have that 4/8 is equivalent to 1/2. Locate 1 on the number line. Label the point and be as exact as possible. Here we are only given the place value of 1/4. Well, I know that if I have 4 copies of 1/4, I will make a whole. So we will take the length from 0 to 1/4 4 times, giving me 1/4, 2/4, 3/4, and 4/4. Labeling our point 4/4 is the same as a whole. Locate 1 on the number line. Label the point, be as exact as possible. Here we have 5 copies of 1/3. So the whole is partitioned into 3 equal pieces, but we have 5 copies of them. So that means I need to split them into 5 different pieces. So I go back 5 and I label my points 1/3, 2/3, 3/3, 4/3, and 5/3. I can now label my point of 3/3 or 1 on the point. The way we have been saying fractions represents a multiplicative operator where we can expand or shrink a desired length. So if I have 2/3 of this unit, we're not quite sure how long this unit is, it doesn't say, but that's okay. I want 2/3 of this, so I want 2 copies of 1/3. So if I break it into 1/3 pieces, I need 2 1/3s. There are 2 1/3s. Notice this has shrunk our original length. I want 5/2 of this length here, meaning I want 5 copies of 1/2. So I need to split this into equal pieces of 1/2, and I want 5 copies. Well, this is only 2 copies. We need 3 more copies. With this, this would be a stretching effect. So I put the 5 copies of 1/2 there. Which is closer to 1 on the number line, 4/5 or 5/4? Let's try to explain. I'm going to use a double number line. Notice that my number line extends to the left of 0 just a tish bit, but also extends to the right of 1. We need to make sure that students know that fractions can lie either to the left of 0 or to the right of 0. All the way, it's just a number on the number line. So I see that the top row is partitioned into fourths and the bottom row is partitioned into fifths. So I'm going to label my points across the top as 1/4, 2/4, 3/4, 4/4, 5/4, and 6/4. Similarly, I'm going to label my bottom pieces using fifths. 1/5, 2/5, 3/5, 4/5, 5/5, 6/5, and 7/5. Now I can identify where 4/5 and 5/4 are on the number line and line them up to see what we can find out. So when I line up 4/5 and 5/4, I see that 4/5 is closer to 1, more so than 5/4. We could use a verbal argument as follows. If we divide the segment from 0 to 1 into 4 equal length segments, each part would be 1/4. We can also divide that same segment from 0 to 1 into 5 equal length segments, where each length would be 1/5. The segments of 1/4 will naturally be longer than the segments of 1/5 because there are fewer of them. The distance between 4/5 and 1 is 1/5, and the distance between 5/4 and 1 is only 1/4. Therefore, 4/5 is closer to 1 than 5/4. Often our go-to is a circle when we learn fractions. But modeling with more than just a circle is ideal for learning fractions, so students can interact with fractions using many different mediums. So let's begin with working with the fraction 3/4. I'm going to use some cube trains. You see along the top I have 1, 2, 3, 4, 5, 6 cube trains. Note then, why would I use 8 cube trains to represent 4? Well, using some reasoning, if I were to split into fourths, I have 3 copies of 1/4, which means that we can represent 3/4 using cube trains or any other medium in many different ways. More than just 3/4, so we're building equivalent fractions even though students don't realize that's exactly what they're doing. Let's work with the Geo Board. I have a 5x5 Geo Board, and this was taken directly from the Geo Board in our interactive manipulatives, and I put a band around the outside. Notice that I now have 4 rows and 4 columns. So if I were to grab 3 of those rows with the yellow binder, I now have 3/4 of my Geo Board circled or squared in a yellow square. So if I partition into 4 equal parts, now you could do this horizontally or we could do it vertically, we would get the same. So I have 3 copies of 1/4 colored in yellow. Let's work with the fraction 3/4 using counters. So I have 3 bears to represent the numerator, and I have 4 bears to represent the denominator. Again, partitioning into 3 copies of 1/4. I see that they're split. So this is very similar to the snap cubes. I just used the straight 3/4 instead of 6/8, but we could have 6 yellow bears and 8 red bears if we wanted to do that as well. We can also use a number line. Notice I don't have anything labeled. I'm going to label 0 and 1, and notice that my number line extends past 1 because we know that fractions can lie anywhere on a number line. I have 3 copies of 1/4, so I need to partition into 4 pieces with 1/4, 2/4, and 3/4. I can see that 3/4 is labeled right there. So as students become more familiar with fractions, again, we want to make sure we extend our number line to the left of 0 and more whole numbers included than 1 to show that the fractions can lie anywhere on the number line, not just between 0 and 1. Partitioning versus iterating. These are some common words that you may have heard me say, particularly partitioning. Means that we reduce the size of the fractional parts but preserve the whole. Iterating preserves the size of the fractional parts but increases the whole. So I have the fraction 3/2, which we know is 3 copies of 1/2. Notice that a circle and a half is our unit. So I need to partition our unit in half first, and I need 3 copies of 1/2. So each part is 1/2. I'm going to iterate by taking 3 copies of 1/2. I notice that I can then take some of my circles and piece them together. I can take these 2 halves to make a whole circle. I have a 4th and a 4th that I could put together with this half to make another whole with a remaining of a 4th of a circle left. So it would look something like this. Our unit is changing into these 12 triangles. I want to find the fraction 2/3 using this particular unit. Knowing that our unit can change and knowing that our unit is very particular, it's not always one, it could be many different things. So we need to partition first. I'm going to partition into thirds because we need 2 copies of 1/3. So I break my 12 into groups of 3, and now I need 2 of those groups, so I'm iterating. Modeling using a variety of different shapes and sizes is also key to show us the parts do not need to be equal to represent fractional pieces. The parts do not need to be clearly lined. The parts do not have to be the same shape, and the shaded region does not need to be grouped into one part. Jamie and Melissa made a hexagon sandwich with pattern blocks, 1 trapezoid and 3 triangles as pictured in the top right. They discussed the fraction of the hexagon modeled by 1 triangle. Jamie says it's 1/4 because the hexagon is divided into 4 pieces. Melissa says it's 1/6 because it would take 6 triangles to cover the hexagon. Both Jamie and Melissa had arguments to justify their answers. Can you comment on their thinking? Which reasoning is closest to your own thinking about this question? Is Jamie correct? Is Melissa correct? Take a moment, pause the video, and think through this a little bit. In my opinion, I would say that Melissa would be the correct one, as I seriously would need 3 more triangles in order to fill up our hexagon. So 1 triangle is 1/6 of the hexagon. Although there are 4 pieces, not all the pieces are the same size. It's important that, again, that our unit is the same. A half of a hexagon and 3 triangles are not the same size or unit. We can use Cuisenaire rods as fractions as well. So notice that there are 10 different ones, each one ranging. The colors are pretty standard. You can change them up a bit, but these are the pretty standard Cuisenaire rods that are used. And it's a way to introduce fractions as well as work with fractions, adding fractions. It also can be used when you're trying to find the least common multiple or greatest common factor, as we'll do in other grades. There is a template that you can print out and color yourself and have your own set of Cuisenaire rods on our site under the manipulatives. So take a peek at that. Perhaps you want to cut some of yours out or use the manipulative virtual manipulatives that we have, which we're going to do here in one moment. So I just grabbed the virtual manipulative of the Cuisenaire rods. The link will be in our manipulatives folder. Our first question is, if the dark green rod is the unit, what fraction does the red rod represent? So I pulled out the dark green rod and I see that 3 red rods can be placed on the bottom to make it equivalent. But I'm only interested in 1 red rod. So 1 red rod is equivalent. This represents 2 over 1, 2, 3, 4, 5, 6. It also could mean 1 over 1, 2, 3, because it takes 3 red ones to make a whole green one. If we keep the dark green rod as our unit, what fraction does the lime green rod represent? So I'm going to toss away I'm going to pull out the lime green. I see that the lime green represents 3 over 6. Or 1, 2, 3 copies, 4, 5, 6. Or 3 copies of 1/6. If the blue rod is our unit rod, what fraction does the dark green rod represent? So the blue rod is now our unit rod, and the dark green is here. Okay. Blue is 1, 2, 3, 4, 5, 6, 7, 8, 9. And our top is 1, 2, 3, 4, 5, 6. So 6 over 9, or 6 copies, 1, 2, 3, 4, 5, 6. 6 copies of 1/9. If the blue rod is the unit, what does the orange rod represent? Notice that the orange rod is longer than the blue rod, but we do know that the blue rod represents 1/9. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 copies of 1/9, or 10/9. If the brown rod is the unit, what does the red rod represent? Or does the red rod represent 1/4? So we need the blue rod. Oops, I'm sorry, we need the brown rod. Is the red rod 1/4? So if I were to cut into 4 pieces, oops, I apologize, I don't know what I did. I think I zoomed in. So we'll put, because if it is, there would be 4 copies of 1/4 would give us a whole. And certainly 4 copies of 1/4 gives us the whole unit of the brown rod. So yes, it represents 1/4. If the orange rod is the unit, put the orange rod out. If the orange rod is the unit, 5 copies of another rod placed end to end represents 3 1/2. Which rod is it? Take a stab and see what you come up with. Did you guess the black rod? If I lined up 5 black rods, I should get 3, oops, and half of an orange rod. I found this particular number line to be especially interesting when we look at unit fractions. There are a few patterns that I noticed, and I felt that it would be important to share with you. I got this from the book Unpacking Fractions. Her name is Monica Nagoy. It's a book by NCTM, and it's really awesome. If you have an opportunity to read this book, it's really worth the read. Further, notice 1/2 is really far off to the right there, but it has to be in with proportion. So there are a few things that we notice as our unit fractions progress. So the unit fraction, as we progress down the line, so 1/2, 1/3, 1/4, 1/5, notice that the unit fractions are getting closer as our denominators are increasing. Further, notice that we are getting closer to 0 as our denominators get larger. Very interesting. Mark walked 2/3 of a mile and then rode his scooter 1/3 of a mile. Which distance is farther? So here we're comparing fractions with the same denominator. So let's start with a bar graph here. So 2/3 is 2 copies of 1/3, and 1/3 is 1 copy of 1/3. So 2 copies of 1/3 when split into 3 are 2 pieces, and 1/3 is 1 piece. I can see now that 2/3 is greater than 1/3. Nick finished 4/8 of his homework before dinner. Ed finished 6/8 of his homework before dinner. Who finished the greater part of his homework? This time let's use Cuisenaire rods. So when I look at Nick, 8 would be the brown rod in both instances because we're comparing the numerators when we have the same denominator. So 4/8 is 4 copies of 1/8, and 6/8 is 6 copies of 1/8. 6 is greater than 4, so therefore Ed finished the greater part of his homework. We can also use benchmarks to help determine which is greater than or smaller than. So I have 4/12 and 8/12. 4/12 is close to the benchmark 1/2 or 6 copies of 1/12, but still less than 1/2. Further reasoning suggests that 8/12 is close to the benchmark 1/2, but greater than 1/2. This can lead us to deduce that 4/12 is less than 8/12, based on their location and how close they are to our 1/2 benchmark. We can also use models, other area models, to compare 4/3 and 4/4. Notice this time our denominators are different, but we have a common or the same numerator. So 4/3, remember, is 4 copies of 1/3. So I have on the left here, the orange boxes, I have a box split into thirds, and I need 4 copies of 1/3, which means that I need a second box of 1/3 to get us that 4. So I have 1, 2, 3, 4. And then I have 4/4, which is 4 copies of 1/4, so all of them get to be highlighted. Notice that the one on the left is more than a whole, and the one on the right is a whole. So we're comparing wholes to wholes here. So 4/3 is greater than 4/4. We can use area models to compare 3/4 and 3/6 in a different way. So again, our numerators are the same, our denominators are different. So I have the same size boxes. 3/4 is 3 copies of 1/4. So splitting our box into fourths, I need 3 1/4 shaded. On the right, I've got 6 boxes because I need 3 copies of 6. 3/4 is greater than 3/6. I can see that more of the area of the boxes is shaded than 3/6. Fractions must relate to the same whole to compare them, so I wouldn't be able to expand that box on the right into something much larger because then we wouldn't be comparing the same thing. So the whole box itself is the unit, and the unit is the same no matter which fraction we're talking about. When thinking of the strategies we have covered, did Helen correctly compare these two fractions? She thinks that 4/8 is larger than 4/6 because 8 is a larger number than 6. Pause, take a moment to think about this, perhaps draw a picture, and come back and we'll see how you did. No, Helen did not do this correctly. Although 8 is larger than 6, we need to think of it as 4/8 is 4 copies of 1/8, and 4/6 is 4 copies of 1/6. So we can use a bar graph. So notice that the entire bar graph is this, or the bar line there, is the same size on the top and the bottom. So the whole thing is our unit. The top is we have 4 copies of 1/8 shaded, and on the bottom we have 4 copies of 1/6 shaded. So actually 4/6 is greater than 4/8. Another way to show using an area model, I have 4 copies of 1/8 shaded and 4 copies of 1/6 shaded on the left. Our large box is the exact same size, just partitioned a little differently because of the 1/8 and the 1/6. But I can still see that 4/6 is larger than 4/8.